Okay, third time's charm. Having a hard time getting this one done. All right, so here's class 20. I still haven't recorded videos for class 19 yet, but I wanted to get the one for the computational fluid dynamics done before the others. So I'm kind of skipping ahead. So this is we're going to use SolidWorks simulation to do a CFD, and we're going to use like our textbook, which is Sengel, and we're going to model some drag coefficients. We're going to try to get the drag coefficient of some of the published things that are in here. And what I decided to do was to do it. What's essentially going to be a 2D problem first, and we're going to use really this one right here for the smooth cylinder, and we're going to try to replicate that drag coefficient. Turns out that it's a pretty tough one, but let's go through it. Before we even start, we should just kind of have sort of a plan of attack of what we're going to do. And I've already filled this out right here. It's got a bunch of things in it because I messed things up. But what I would recommend is you first have to decide, well, we were going to do the smooth cylinder. Then you have to decide, well, what we're going to try to aim for, like what Reynolds number we're going to try to do. I think, because I had problems over here in 10,000, that I'm going to go for 1,000. So I'm going to go, 10 to the third Reynolds number, and we're going to try to see for a smooth cylinder, we're going to expect a coefficient of something like about 1, right, the drag coefficient. So I went ahead and decided I was going to use metric units, and I'm going to use water. And so I decided on a 1-inch diameter, which comes out to 0.0254 meters. And I'm using the density of water here of 999 and a viscosity of 1.12 e to the minus 3. And if I use those parameters and I'm trying to get 1,000 a Reynolds number, I end up with a velocity right here of, let's call it, it's really 0.04414, 0.0414. I'm gonna double check that I got the. I know this is silly, but I'm gonna double check that I got the number of decimal places. Yes, okay, 0.04414. All right. So that's the plan of attack. So we're gonna start a new part. And I'm going to make sure that I'm in millimeters, because I'm going to take screen grabs of the things as I document it. I would like to have a white background, so I pull that down and go to a plain white background. And this is going to be a cylinder, and I'm going to have X direction be the direction of flow. So I'm going to create it on the right-hand side. Is that correct? Nope, I got to correct it. I made this mistake before. It's on the front side. Right, that's the cylinder is going to be going into the page. And so we're going to create a sketch and make a circle. And you might, if you need help, let me know. Getting some SolidWorks skills back in, because you might not have used it for a while. And now I'm going to dimension this and make it 25.4 millimeters. And then I'm done with my sketch. And now I can extrude it. And I'm going to extrude it in both directions. So I need to grab a hold of the sketch, and I'm going to go 10 millimeters in this direction out of the board, and I'm also going to go 10 millimeters in that, so that I can use the front plane as like a centered plane onto the thing. And actually, this is all we need for our model. But something you might want to do, you can either do it this way right here, or you can use the snagging tool. I like that tool. And you might want to just take a screenshot of this piece and put them into your Word document, because you want to like be collecting things as you go along. It's sort of a silly thing to do, but we're going to have a description in the beginning, in the introduction, of what our thing will be. That uses a lot of blank space, so you might want to like crop that down, right? So that's just a little hint of something to do. And also, a lot of times I think it's better just to let these guys float right in here. And as you're going along, you might want to go ahead and put in the figure description underneath. Might call it figure 1, and just model or give it some more description. All right, I'm just not going to write everything that we need to do right here because the video is going to get too long anyway. Also, I don't think you should have a fill. Whoops, I'm sorry, that's on the text. Let's see, what am I going to do on that box? Can I do the box? Oh, I can't. Sometimes I can't stand this stupid thing. I can't contextual right-hand click format shape and have no fill and then no line. There you go. But we could reuse this. Let me move this back up to there. We could reuse this caption below here. Just a nice little thing to stick in there because sometimes to make it a little bit more compact and look more professional. But anyway, we will be using this some more later on. Continuing on here, we should save this, and I already made one, so I'm going to call this cylinder 2 in my project. And now we're ready to do our SolidWorks simulation. 6 minutes into this? Really? Did I take that long? Jesus. All right. Anyway, we want to make sure that we have the add-in of the SolidWorks flow simulation. So click on that little guy next to the gear and scroll down, and you'll see that we have SolidWorks flow simulation. Click him here on the left. If you're going to use the same computer, right, click him on the right as well. But we'll get that initialized, and you'll find it underneath Tools and Flow Simulation. And we're going to go to Project, right? So Tools, Flow Simulation, Project, and then go to Wizard. And maybe name this cylinder drag RE equals 1,000 this time, right? Because I had problems with the 10,000. Hopefully this will be better. I'm going to go to Next. And on the next one, we're going to define our units as SI, meters, kilograms, seconds. We don't need to change anything down here. We're going to take external flow here at the top. And I'm not going to go time dependent, but we could do something along those lines, but we're not going to. Go to Next. I'm going to pick my liquids, and I'm going to pick water. We can add him down below. We're not going to do cavitation. You notice that we are picking laminar and turbulent as default. Let it be. We're not going to change anything on the wall conditions. We're going to keep the roughness as 0. It's smooth. And right here is where we're going to put in our velocity. And Mr. Small Attention Span can't remember what he had. 0.04414. All right, so right here is where we're going to put in the 0.04414. Okay, and we can finish. Now, we have this tree over here on the left-hand side. The stuff on the top, we can move multiple simulations onto the same thing, so just be aware of that. But we're already in this one, and you can see we have different little topics to come down. The first one I want to change is I'm going to edit this domain, and I don't like, I think it's going to be easier to go 2D. And you can see that it makes the thing two-dimensional. And it gives it boundary conditions that make it symmetry over the side. It is two-dimensional, but it does have a thickness, and so this messed me up before. Notice that it's 0.002 and 0.002, right? So it actually does have, it's not exactly two-dimensional. It actually has a dimension into the board, but it has a symmetry boundary condition. So just be aware of that. And one of the important things, we have to have goals. It's so funny. Everybody has to have goals in life, but we want to insert some goals, some global goals. And the most important one to start with is the force in the X direction, right? Because that's really what we're looking for, is the drag and the flow is going in the X direction. So we want to have the force in the X direction. So we accept that. And then underneath, and then on goals here, we also want to insert an equation goal. And what we're going to do is we're going to make the drag coefficient. So let's make that drag coefficient. And we need to take the force, so we're going to click on that. And you'll notice that it shows up down here in the calculating thing. And we're going to need to calculate the drag force. Now, I wish there were some more automated things in here. I think there ought to be. And maybe I'm just not aware of it, but the resource that I have that I'm basing this on didn't give me any clue on how to do that. So what we're going to do is we're going to type out an equation. You can see here's the from the example that I was basing the thing on. So we're going to have the drag coefficient. We're going to take that drag force we just found, multiply it by 2, divide it by density, divided by the velocity squared, and then divided by the area. And the area in this case is going to be the area that it will see in that direction right there, right? So it's going to be the diameter times that thickness, because it's going to be a rectangle that we're having as our cross-sectional area. So just be aware that you want to change the thing out. Like if it was a penny in perpendicular, the way we would have done it would have been that diameter divided by times pi, diameter squared times pi divided by 4. Whew, tired. Okay. So we're going to multiply that by 2, and then we're going to divide it by the density, which is 999, and also we're going to take the velocity. Let me go to the area first. So we're going to have 0.004, right? That's the width, is the two thicknesses there of the sides, and then also the diameter, which is 0.0254, 25.4, and then why did I do that for? Wait a minute, let me think first. Yes. Okay, got that right. Times 0.0254, because that's the it's 1 inch in diameter is what I had chosen, and then multiply by the 0.04414, and then squared. I think I got that right. Right. So density, here's the width times the height, so that's the area, and then you got the velocity squared. And you should make this have units of, anyway of that, but dimensionless LMA. And so that's correct. And we go, okay. And now let's say to adjust the mesh. Let's take a global mesh, and this one's already set at 3, right? I would say let's crank it up to 4 here. And we can, by the way, we could take a look and we could see the mesh. We could go show basic mesh, and you can kind of see how big they are. We might want to refine the mesh, and we're going to try to do that a little bit, hopefully, in this video. So we're ready to go, actually, and hit run. And we're going to solve, and everything's good right here. It's going to bring up another window, and we're going to try to get over there fast so we could see it, because it's going to solve pretty fast right here. Boom, you can see, and I already had this thing clicked up. So see, this one went so fast, there wasn't even time to have this display show up, which is a button right up here, and then also this graph, which presented down there. So let's see what we got for our results. Let's get that thing perpendicular here. And so we're going to go up, and you can see, by the way, note that the thing says 24.FLD. That's because I've run like 24 different runs. So it's just creating folders that it stores the stuff in. But a lot of times this thing will say not loaded, so you might have to hit the load button. But it says unload right now. We're going to create some graphs. So we do the insert under the cut plots, and I'm going to pick the front plane, and I'm going to pick contours. We could also have vectors, by the way. We have vectors and contours. That's a good look. And we're going to take velocity here. And I believe we're going to be able to, let's see, velocity. We're just going to overall velocity, not going to have x velocity. And we can change some of these things later. So let's just see what we get. Boom. So we got these little tiny velocity vectors. I kind of like them. You kind of see how they're working around there. Kind of small inside here. Something I also like to add. Well, first off, let me talk a little bit about this graph right up here. I think it's good to change these and make them consistent. So you can edit this, and you could pick the values. If you're increasing it from one to another, it might not make sense to do what I described before in class, which is to make a consistent mark all the time, but you do want to make them so that they can be read, in my opinion. Also, I might have just chosen somewhere previously, and it's saved as one of my preferences, to have this discrete breakdown. I think that's much superior to having the merged type of colors, right? Let's see, no, I don't want to do that. And so anyway, I'd like to have like maybe make this like 0.06, and then if you can, maybe make this like 12. But it doesn't seem to have worked for me to make it very even. That's still not quite even. So I don't know. Maybe I just can't do math. Yeah, see, that's actually better right there. So one more in addition to that gave me a graph that had logical increments, and I really think that's an important thing. You can also make this horizontal sometimes to get the thing out of the way so that you could see it. Or now, there you go. Okay. So in terms of making your report, this might be a good time to do a screen capture. And so we could put that into our report. We also, by the way, let me go up to, oops, let's get moving this guy around. And you could, we might want to also, as we're coming along, put this guy down in there, and just get as much as we can get done. Contour plot RE equals 1,000 CD, and we should make that subscript when we get a chance, right? So make it subscript now, subscript CD, and we don't know the CD yet. We have to find that from our results. We might also, by the way, have show basic mesh. Well, let me actually hide these right here. Let me hide that, and I might show basic mesh, and we might screen grab that too, right? As in terms of our documentation. And so this becomes figure 3, doesn't it? All right, so we might be doing something more complicated than this. This is the simple one that I'm doing right here. Grid mesh, rough grid mesh, right? Or first attempt, something along those lines, right? Something that will help us to understand what it is that we're looking at if you happen to be someone reading this report, right? You get an idea of what the steps were and what each of these things are, all right? So let's see. The next thing we want to do is actually get a value. So I'm going to go to surface parameters, and I'm going to insert a thing, and this will stay in there. And I'm just going to click all. And you might even go like more parameters if you needed to try to find it. And I really wish they had one of the parameters to be the drag coefficient, but we're going to calculate that on our own anyway. And so what we could do is go to export to Excel. All I need to do is select a face. In here, let's select that face right there. And now we can export the drag that's on that face. It's going to figure out the forces, and an Excel thing is going to pop up. And we're going to get that X component's the only one we care about. So there's the force. You can see there's other things. You might want to notice that they have a different density than we did. And you might want to go take a look at the viscosity. You can see that the viscosity is different from ours. So we might actually want to update our thing. But unfortunately, that updates the Reynolds number as well. And we don't have a nice even Reynolds number. But if you want to be accurate, that's what you would also do. But for right now, we're kind of stuck with a little bit of... we're going to see how off we are. And it's going to be considerably off. So I'm going to hit Control-C, and I am going to now put that over into, I already have this arranged right in there. And so I'm going to put them right in there. So that's my force. And now I already have it calculated, but I'm going to calculate it for you again. Here's my drag coefficient, and it's the same equation as we had before, right? But now we're going to use the stuff up here. And like I said, we probably, if we're going to be accurate, we should update what these things are. And that would update, we would need to update that Reynolds number. Right? But let's go ahead and continue without it. And so I'm going to go equals, and I'm going to take that drag force times 2 divided by the density. I'm going to hit F4 so I can keep using that cell again. It's going to be divided by 0.004 and also divided by my diameter, and I'll put F4 so it always goes back to that cell, and then lastly divided by my velocity, which, I'm in the wrong spot. I should have been down below 1. Well, I'm going to move it. I'll move it in a second. And that one always gets things. So we're going to square it. So this is going to be very wrong, but I'm going to copy this down below and copy this down below and get rid of that. Okay, sure, whatever. 0, boom. All right, so you see that I got a spot right here, which wasn't very good. All right, that's going to be the 1,000 that I used. So I'm going to want to try to improve that. And the best way to do that, okay, we're at the 21-minute mark. So right there, that's probably a pretty good start, but we want to do that something else, right, kind of thing. If you notice up above, I actually have a graph up here, and for this 10,000 point, I really went to town and kept increasing this local thing, and it really bogged the machine down, but you could see that it converged eventually, and it was getting better and better as we were going along. But this is the drag force that I was getting initially, so you can see how bad this was over here. That was not the right one. I'm trying to figure out what was the right one then. I'm not sure now. Oh, I know that this was actually the drag coefficient. I'm sorry. These were the drag coefficients, and so you can see how far off the initial one was. It was down here. It started to move back up, but still never did make it back up to the line. Although I did one at a Reynolds number of 10 and was able to get it fairly close up there. Of course, that's pretty laminar actually. But anyway, so let's see how we can do to improve this. Right, so we have, by the way, we have this done right now, and there's a lot of things we can do now that we have this done. We might want to do the refinement first, but what we could do is we could do this thing called a clone, and you could make that an identical copy of, so let me just do the clone, and let's say that we wanted to do 10,000, right? So I'd go 10,000, and I'd say okay. And now this is the active one, and notice there's no results loaded into there. What we want to do here to update and make this 10,000 is I would come into the input data, right click it, and go to general settings. And I would have my initial conditions. I could go down to here, the initial conditions. You can see that's where I can change my velocity right here. And you're okay right there. Another thing that we could do is we could go down and update our equation goal, which also had the velocity in there. So we need to get rid of that right there, right? So 0.4414 is going to be the one, and you can check it over here, by the way, right here. So 0.4414 is going to be the 10,000. And we could actually just run this. We don't have to do anything else. Say run. And we could watch it. Oh no, it's over there. Or it's done already. Boy, that was fast. I mean, you know, this it's really easy to when something goes that fast, right? See, you can't really see much difference in between this. Okay. But we can now just go back and we could just look at that plot. Could show it. Probably need to reset this, edit, and maybe I'll make it 0.6. There you go, boom. And actually it's not going to look all that much different, right, from that one right there. It doesn't look that much different, but it's a different scale, right? That's really what we have. And then we can also like go down here and edit definition again, and just hit export to Excel again. And now we can grab a hold of the X component of the force. And I'm going to overwrite the one that I had before, even though I put so much effort into it. Actually, maybe I'm going to put it right down there. And I'm going to grab him and I'm going to save him for later. So I'm going to bring him and put him right there. Boom. So you can see how bad it was, right? So that was not good enough. And we're going to try to explore why was that not good enough. And so here's the method about going here. So I'm going to stick with the 10,000 now. We're going to try to improve that. But probably the better idea was to before we cloned it, would be to do this refinement and then clone it, because then the refinement's going to carry over. So what we could go is go to the mesh right here, and we have a couple choices. We could click on the global mesh, and we could improve that. So let's see what happens. Let's go ahead with just a global mesh of like, let's just bring it all the way up to 7. Let's see what happens. And I think we could go ahead and hit create mesh. I don't think it's going to actually do anything. It's done over here. Another window comes up, by the way, when the mesh is created. And by the way, it gets rid of rid of the results when you just do a mesh. And underneath the cuts, let's insert another cut that only shows mesh. Nothing to display. Okay, because it's a global mesh, right? That's why. We'll do the local mesh in a second. But we can just run this again. It'll probably go pretty fast. Let's see how fast it goes. Whee! You can see as it blending through. Ooh. See, this is probably some of the issue that I had, is you can see that it has a vorticity. You can see the vorticity taking place. And that's a time-dependent problem. And so probably one of the reasons why it wasn't working very well. That's good because it's kind of diagnosing an issue right there. But it did come to a solution, so we could get this answer. But be aware that it's not we might be suspicious of it. So let's show the answer there. And actually, look at that. You can see some of the vorticity was taking place. That's interesting. You can see the arrows and that kind of thing. All right. So let's see what happened with the values. So we can export to Excel, and let's see. Did we do any better? It got a larger number. Didn't get up to the number from my previous one where I was like crazy refined. I'll plug it back in. You can see it got better up to there. But let's see what we can do. Let's see how much better we can do. Let me get rid of some of these files, some of the Excels that are open here. Oh no, it's getting mad at me. Let's see, I don't know if I did. Let me get rid of my office hour. Nope, failed. All right, so never mind. All right, I could wait. You could wait. I'm trying to plan out my schedule next semester. They want me to move one of my classes. All right. So let's see. We could go down here. Let's do the local meshing. So we haven't demonstrated that yet, and we can't do so many to go to convergence. It turns out it takes a lot. But we can go to this mesh right here and insert a local mesh. And there's a lot of choices, and I'm not sure what the best way of approaching it is, but this is the way that I did it. We don't have any channels. Channels mean gaps in between things, and we don't have any gaps in between things. There is advanced refinement. I tried that one a little bit. Not really sure I liked it so much. So we're going to turn that one off. But I'm going to go to equidistant. I liked him. And I went 3 layers deep. And then now the scale of this, I tried a couple. I thought 3, I went it up high and really, really bogged down the machine when you get up really high. So be careful on that. you're going to crash these computers. And you're going to think about like the gaps, and there's 3 different gaps right here. And this thing is all of 200.02. So maybe I'll make that 5, and I'll make this one on the scale of like, well, I don't know. I got to be careful not to get not to get like larger than the yeah. So I might actually bring that some down to like 2, and come out that to like 10 millimeters. I think maybe make up this to I don't know, like 15. I don't know. Let's see what that does. Let's see what that looks like, and we're going to create a mesh. Hit right click mesh and hit create mesh, and it's going to destroy everything else. And it said it is done. It's pretty easy right there. So we're going to come down to this, and underneath here it says mesh only. I'm going to hit insert and then a mesh plot. And now you see here's the refined mesh. And let's see. And because this thing had a tail that was moving, I kind of think that we ought to have some mesh, detail mesh down here, but I haven't figured out how to do it just yet with the controls, because the only thing I see here is insert local mesh. There should be a way to do, let's see, what is it? What does that want to say? Best mesh? Basic mesh color, okay. But let's run this and see how much better it does. It's going to take longer though. So let's take a look as it's doing it. You can see how it's starting to grow. And remember what this is doing. Right? This is I'm taking a grid and it's doing this numeric method where it's crunching. And look at this thing. Oh, blows, explode up. And once again, I think it's doing the tail. So it's doing like the Struhal thing. And this is an unsteady characteristic right here. So it's, boy, it is really cool though. I like to watch the thing as it's number crunching. So don't have a ton of confidence in this answer, because we might need to do the time dependency thing. And I don't know how much that's going to mess us up. And in terms, we would actually have to get a time steps, because it has a time dependency, and look at the results for a particular time step. Yeah, we're looking. Yeah. So once again, I'm got a lot of. I'm not savvy enough to tell you how to proceed with that, but we can read these results. We can show them right there. We can see what they are, and let's see what we had in terms of our improved or not improved. Let's see, or how much closer we got to the published or the expected Reynolds number. Excuse me, not Reynolds number, but drag coefficient. That's pretty good. All right, looks like it's a larger number. That's a good thing. And putting it back up in here. Boom. Oops. Look at there. I think I just hit can copy instead of paste. So here you go. Copy. And over here. And paste. Here's the moment of truth. Ooh, we got pretty close. So there was a mesh refinement. And we can continue with that. And you can see how I tried to converge this. We actually got better here than I ever did by a whole bunch of convergences. So the global really did help. And then combined. So I was almost up to 1.05. And so we started getting pretty close. So that is some of the things that you can do with this with this code. And to finish up with the thing, we might also take another screen grab. Let's see, I should do this and not that. I should do it right here. Boom. And maybe have that with and then make sure that you're writing the things out in here like this. I don't remember what that was right there, but this was a different Reynolds number. This one, right? Oh, by the way, that thing messed that thing up. What happened here? Why is that? I hate it when that happens. It shows the top of the thing. I wonder why it shows the top of the thing. But crop that sucker off if you got that going on right there, right? So if this happens right there, make sure that you crop it and get the most out of your figure, right? Same thing up with this guy. And make sure you keep the scale in there, but you might want to center these and make it look good, that kind of thing. Try to make these look kind of the same, and I can't remember what that drag coefficient was. But yeah, I want you to like compare the drag coefficients to what had been published. Let's see, I'm trying to get that guy on there. Here's like figure 4. Yeah, I forgot to continue with this as we were going through, so shame on me. But that's what you should be doing. Like another thing, we could have like hide this and then show this, so that you could show a thing of the screen capture of this piece. But you get the idea. And tell a story, but not like a story, a narrative. Give it provide information so that people who would read the white paper could know what you did and how you did it, and your thought processes, and then also when you include the results, what they mean. So anyway, my video is way too long. Hopefully this will give you enough guidance to do the project. Maybe I'll make another one because I have a couple other models that I could run that might be informative. Like I have I could just mimic what they had done for a airfoil. So that's it, and good night.